Grade 11 and 12, we're still continuing with Euclidean geometry, and this is our session 4, and we're gonna be focusing on theorem number 4. Okay, without any further ado, let's just get straight to it. Okay, so theorem number 4 states that the angles subtended by the same arc or chord in the same segment are equal. All right, so in other words, if you have the angles in the circumference that are subtended by the same arc, or rather the same chord, in the same segment, then those angles will be what? Will be equal, right? As you can see also in the statement here, it says if the angles are subtended by the chord of the circle are on the same side of the chord, right? That is, they are on the same segment, right? For example, if I have a chord here, rather AB, right? Let's take AB as our chord, and we have angles that are subtended by this chord, right? On the same segment. Remember, this is the smaller segment and this is the what? This is the bigger segment, right? Okay, so we are having angles that are subtended by this arc AB. In the circumference is this angle C, and the same arc, the same chord is subtending another angle, the circumference, in the same segment, right? So the theorem states that those angles will be what? Will be equal, by the reason that they are angles in the same what? In the same segment, right? Not only subtended by a chord, they can also be subtended by an arc, right? For example, if you can take a look at DC here as your arc, it's subtending an angle at the circumference, there it is. It's the same DC is subtending another angle at the circumference. Because these angles are in the same segment, then they will also be what? They will also be equal. So that's exactly what the theorem says. All right. Okay, so how can we now prove this theorem? Remember, it's saying this angle here will be the same as this one, and this one will be the same as this one, because these are angles that are subtended by the same chord in the circumference, right? So they are actually angles in the same segment. Okay, let's say for instance we want to prove that angle D is equals to angle C, and I'll just quickly show you how to prove this theorem. So we're just gonna start with construction. So on your construction, you join the radius, right? From this point, we are forming radius join line from A to O, and from O to what? To B. So we have just joined those two lines, right? Remember, we are required to prove that indeed angle D is equals to angle what? Angle C, right? We want to prove this theorem that if we have angles subtended by the chord of the circle that are on the same side of the chord, then they are equal, right? So how can we prove this? So to prove this theorem, you have to relate it with theorem number 2. Remember, we did theorem number 2, right? And we said theorem number 2 says that the angle subtended by an arc at the center of the circle is 2 times the angle subtended by the same arc at the circumference. All right, so it means that I can now come and say angle AOB, which is my angle at the center, will be equals to 2 times angle D, right? Because it's also subtended by the same arc at the circumference. Okay, so it's 2 times angle D. So we can see that, and by the reason angle at center is equals to 2 times angle at what? At circumference, or rather theorem number 2, right? But we can also see that angle AOB, this one, is also equals to, look at this, it's subtended by arc AB at the center. It's also the same arc AB is also subtending angle C. So it would be 2 times what? 2 times angle C, right? By the same reason, angle at the center is equals to 2 times angle at the circumference, right? Now we can now come and equate these two things, right? Because they are both equals to angle what? AOB, meaning that 2 angle D is equals to 2 angle C, because what? Both of them are equals to angle AOB. Look at this. If we divide both sides by 2, we can finally deduce that therefore angle D is equals to angle what? Angle C. To prove that indeed angles subtended by the same chord or the same arc in the same segment at the circumference, they are what? They are equal. Okay, let's take a look at an example. Okay, example number 1. It says solve for x and y given reasons for your answer. Solve for x and y given reason for your answer. You just have a diagram there, right? Okay, how can we solve for x and y now? Okay, look at this, very interesting. Can you see that we have angles in the same segment, right? We have the angles in the what? In the same segment. Look at this arc here, MN, is subtending a certain angle at the circumference, which is 20 degrees. Can you see? But the same arc MN is also subtending another angle at the circumference in the same segment. What did we learn? Angles in the same segment subtended by the same arc or chord are what? Are equal. Okay, meaning that our x will be equals to 20 degrees by the reason angles in same segment. Angles in same segment. Alright, let's go and solve for y. So for us to solve for y now, let's take a look at this arc here, right? What is this arc subtending at the circumference? It's subtending y. The same arc is also subtending 15 degrees, and we know that angles at the same segment are what? Are equal, meaning that our y will be equals to 15 degrees, but there is an angles in what? In same segment. All right. Okay, let's also take a look at this interesting, quite relational example. All right, so you are given that FH is parallel to EI, right? And we can see they use parallel lines there, or rather the symbol for parallel lines to show us that, right? Okay, so they're saying E angle IF. Where is E angle IF? Is this angle here. E angle IF is equals to 15 degrees, and they've indicated there, and they're saying determine the value of B. They want the value of B now, right? They want the value of what? Of B. How can we solve for the value of B now? Okay, so if immediately when you see this thing like an oxbow, do you call it oxbow tie or something like that, where its four corners are connected to the circle, you have to think about theorem number 4, right? Immediately when you see those zigzag kind of thing where the four corners are connected to the thing there, to the circumference, you have to think of it, right? So obviously we can see that there's this zigzag, or maybe let me just use a different color to show you. Can you see that there's this sort of like an oxbow tie? I don't know if you call that an oxbow tie, something like that, where we can see that there's an arc subtending an angle at the circumference, the same arc subtending another angle at that circumference, meaning that our B here is the same as this angle F there, right? Meaning where there is F, we can put what? We can put B. Okay, so yellow is not quite clear, so this angle is the same as this one, so we can put B there, right? Okay, we can see parallel lines, and immediately when we see parallel lines, we have to recall the Euclidean geometry basics that we started with in session 1, right? We said when you see parallel lines, 3 things must come to your mind. You have to be thinking of alternative angles, you have to be thinking of corresponding angles, you have to also be thinking of co-interior angles, right? So for our case, because we want to solve for B, what can we use to solve for this B? Can you see there is something like a Z there, right? That incorporates that B with another angle. So we have to be thinking of what? Of alternative angles. Then we can deduce that angle B is also the same as 15 degrees. Okay, let me just put this down. We are saying angle B is the same as angle F, or rather let me say B is also equals to H angle F I, right? because these are angles in what? In same segment. That's what we started with, to say this arc is subtending an angle, the circumference. The same arc is subtending another angle, the circumference. Then they are equal because they are subtended by the same arc at the circumference and in the same segment. All right. So, but we know that angle HFI is the same. This one here is the same as what? As 15 degrees, right? But by which reason alternative angles are what? Are equal, and we have to give them the lines that are parallel because FH is parallel to EI, right? So that's our reason for that, right? Then we can deduce that therefore B is equals to what? B is also equals to 15 degrees because both of them are equals to what? Both of them are equals to angle HFI, right? So that's basically how you can solve for that using this theorem number 4 and also incorporating the geometric basics that we did in lesson 1. All right. Okay, let's take a look at this very interesting example. So you are, and this was adapted really from Department of Basic Education, November 2015, 11 paper 2, and it was your question 9 there, right? So they are saying in the diagram, O is the center of the circle, diameter Ln subtend Lkn at the circumference of the circle. M is another point on the circumference, and chords Lm and Km are drawn such that Km intersects Ln at O, and you are given that your angle M is equals to 55 degrees. So what do you do when you are given such kind of a problem or question? So what you do is you have to be thinking of all the theorems that we did from session 1 in this question, right? So before going into answering the question, it is very advisable that you start filling up all the diagram using the theorems that we have learned so far. All right. So now your relational approach it's needed in this case, right? So the theorem number 4, we did theorem number 4, and we saw that in theorem number 4, if there's an angle subtended in the same segment by the same chord in the circumference, then those angles will be equal, right? And we can see here LK is subtending an angle here which is M. The same LK is also subtending another angle here which is N, right? Or rather you can look at that oxbow sort of like thing, and the four corners must be connected to the what? To the circumference. So we don't want you to go and say, if you are given something like this and you start saying this angle is the same as this one, it's totally incorrect. We said the four corners must all be connected to the circumference. In other words, it must be sort of like a cyclic quadrilateral, right, where its four corners are connected to the circumference. Then you can go and deduce, oh, this angle is the same as this angle here. It means here we have 55 degrees by angles in the same what? In the same segment. Okay. Look at this here. Ln is what? Is a diameter. What do we know about a diameter? Angle subtended by diameter at the circumference is a what? Is a right angle. And this was our theorem number 3. Remember? The one we did yesterday. Alright. So we said angle subtended by the diameter at the circumference is a what? Is a right angle. And we see that it's an angle in semicircle. All right. Is there anything we can calculate here, or is there any theorem we can apply? I think that's all for now, and we can just go and answer the questions now. All right. So they want you to determine number 1, calculate given reason the size of angle NKM. LKN, we have already calculated it, right? We know that this is what? Is 90 degrees because it's angle in what? In semicircle. Angle in semicircle. Remember, angle subtended by diameter at the circumference is a what? Is a right angle. Or someone can say angle subtended by diameter. Alright, so that was quite very simple. Okay, let's go to number 2. They want you to calculate angle LOK LOK. So it's this angle here, right? They want you to calculate this angle. How can we calculate that angle? It's angle at the center, right? You must be thinking of theorem number 2 now, right? What do we know about theorem number 2? Angle at the center is 2 times angle subtended by the same arc at the what? At the circumference. All right. Okay, so let's go and identify the arc. Here is the arc, right? It's subtending an angle at the center. Here is it. The same arc again. It's also subtending another angle at what? At the circumference, meaning that our L or angle OK will be equal to 2 times angle at the circumference, which is what? Which is 55 degrees. All right. So by the reason angle at center is equal to 2 times angle at what? At circumference. So you must be thinking of all these theorems, right? So 2 times 55 degrees is 110 degrees. So there we can put 110 degrees. Okay, let's now look at number 3, the last one. They want you to calculate angle L2, right? Angle L2. How can we calculate angle L2 now? All right, how can we calculate angle L2? We know that here we have an exterior angle, right? Look at this triangle here. You have an exterior angle and you have this L2 and this 55, right? So you must be thinking of those geometric basics. They are very, very important when you are solving Euclidean geometric question, because if you can check here, we are using most of them to answer and some of the theorems that we covered in the previous session. So you must not think of this theorem independently, but you must think of them as integrated. Just think of them in a question. If you see something that wants you to apply the previous theorem we did in session 1, session 2, session 3, or so on, you must be thinking about it. For you to be able to have this kind of knowledge, for you to be able to relate those other theorems, you must practice a lot of questions. All right. Okay, so let's go and calculate our L2. We know that if we use exterior angle is equal to sum opposite interior angles, then we'll have that our 110 degrees will be equal to our L2 plus what? Plus 55 degrees. And we are saying exterior angle of what? Of a triangle. We know that is equal to the sum of the two opposite interior angles. So 110 degrees minus 55 degrees is equal to our L2. Then our L2 will be also what? It will also be what? 55 degrees. Can you see? Our L2 is also 55 degrees, right? 55 degrees. Or someone might have chosen not to use this long method, to just simply say, oh, this is the center, right? And we know that this is a radius, and we also know that this is a radius. So L2 is obviously 55 degrees because base angle of an isosceles triangle are what? Are equal. So someone can choose to say L2 is equal to 55 degrees because angles opposite equal what? Equal sides. And you must show them the sides that are equal because OM is a radius that is equal to OL. All right. Okay, so let's now quickly take a look at some very, very, very important deductions that can be made from theorem number 4, right? And we call this corollaries of this theorem, right? Corollaries, or rather the deductions that we can make from this theorem, right? So number 1, one of the deductions that can be made, and it's very, very important, is that equal chords will subtend equal angles at the circumference. This is very, very important. We are not saying somewhere inside this circle, right? We are saying at the what? At the circumference. So if you have your A and your B, and maybe C, D, E, F, and because CD is a chord equals to EF, we can say therefore, we can make a deduction to say therefore angle A is equals to angle what? Angle B, because we have what? Equal what? Equal chords, right? And that will be your reason because we have equal chords. So we know that equal chords subtend equal angles at the what? At the circumference. Very, very important. Number 2, equal chords subtend equal angles at the center. Also, they subtend equal angles at the what? At the center. We are not saying these are not vertical opposite angles because it's not x here. Can you see? Something like this, and it goes like this, and here you have like this, like that. So, but the fact that this chord is the same as this chord, they will subtend equal angles at the what? At the center. All right. Number 3, very important, equal chords of equal circles subtends equal angles at the circumference. All right. So if you now have two circles now, all right, they can try to trick you. They give you 2 circles. This is the first circle and that other one is the second circle, right? And you have that they have equal chords, right? So similarly to number 1, they will also subtend equal angles at the what? At their circumference. Their angles will be equal. Okay, let's just take a look at some quick example for you to conceptualize this. Example, so it says solve for x, and they want you to solve for x in both these 2 diagrams. All right, so let's start with this first diagram in blue. They're saying solve for x. How can you solve for x now? Right, look at this, very, very interesting. They tell you that angle, line BC is the same as line what? As line AB, right? And those are chords, right? This chord is subtending an angle x at the circumference. This chord AB is subtending an angle 15 at the circumference. What did we learn? Equal chords subtend equal angles at the circumference. It means that our x will be equal to 15 degrees because we have equal what? Equal chords. We know that equal chords subtends equal angles at the circumference. Maybe you can tell them the chords that are equal, AB is the same as what? As BC. All right. Okay, so that was quite simple. Let's come to this one in red. They want you to solve for x also, and let's go and solve for x. What can we see? We have a chord here, right? And this chord is the same as this chord here, right? But we don't have a center, so we don't want someone to tell us that this angle is equal to this angle because of equal chords. No, that is because of vertical opposite angles, right? But in terms of because of the chords, this chord will subtend an angle at the circumference. There is it. It's angle S1, right? Then we can deduce that is equals to what? This chord, this side, is subtending another angle at the circumference, right? And there's that angle, the circumference is angle what? It's angle P2, right? Okay, so we can now go and solve for what? For x. Quite very simple if we do it like that. All right, so how can we solve for x? We can relate this with theorem number 4. We say that angles in the same segment are equal. Can you see? Angle x is the same as what? Is the same as angle P2, right? Because these are angles in what? In same segment. These are angles in the same segment. Those oxbow, sort of like an oxbow zigzag shape there, where it's 4 corners are touching the circumference, and or rather we can use this arc, or rather this chord, to say this chord is subtending an angle here at the circumference. The same chord is subtending another angle there at the circumference. Then they're equal by someone can say equal chords, or rather can say angles in the same what? In the same segment. Okay, so but we know that our angle P2 is equals to angle S1, right? Why is angle P2 is equal to angle S1? It's because we have equal chords, right? This chord is subtending an angle, the circumference, which is S1. And again, this chord SR is subtending another angle, the circumference, which is P2. So because of equal chords, those angles are equal, right? So equal chords, and we can tell them which chords are equal because PQ is the same as SR, right? Okay, so where there is P2, I can go and put X, and where there is SR, I can also go, S1, I can put X, right? Then to solve for X, very simple now. We can just use vertical opposite angles here and put 35 degrees there and use some angles of a triangle and solve for X. All right. So we have to tell them whatever we are doing. We are saying T1, or rather angle PTS, is equals to 35 degrees because this is vertical opposite what? Opposite angles. So we just want that smaller triangle now with all what? With all variables and values so that we can solve for X. So now we have filled that triangle. We can now go and solve for X, right? To say X plus X. Okay, let me put it here. Sorry about this. X plus 35 is equals to what? Is equals to 180 degrees. Why? Some angles of a what? Of a triangle. You have to be given reason because you find this question has 5 marks, right? And as you are given reason, you are getting some marks. Okay, so 2x will be equals to 180 degrees minus 35 degrees, which is 145 degrees. Then 145 degrees divided by 2. Then our x will be equals to 145 degrees divided by 2, which is 72 point what? 72.5 degrees. All right. Okay, grade 11 and 12. Thank you very much for joining me in this session. And this marks the end of our session. Coming up next is Theorem 5 and 6. We're just going to do Theorem 5 and 6 all together in our upcoming next session. Otherwise, that's all for today. Thank you very much for watching and goodbye.